I posted solutions to 1.3 examples, but I wanted to go over the solution for question D, just in particular because I find that this is a problem that while students might intuitively believe that's true, putting together a rigorous argument can be a challenge. So I wanted to walk us through it and kind of model how I think about these things. So first of all, I want to point out here that we're going to be using Lemma 1.3.8 to try to approach this problem. And that's because one way you might think about this is when you look at your claim, your goal is to produce the existence of an element that's an upper bound for A. And so if we're matching conclusions, something that we might want to notice here is that this assertion gives you an existence statement. It gives you that a little a has to exist in the set that you're working with. Now, I'm looking for a little b in the set B, but remember, I could go through this and I could talk about the set B here. I could be talking about sup B. This could be a little b in B, such that s minus epsilon is less than b. It doesn't matter what you name the set. The other thing I want to point out here is that remember what this statement is saying altogether. It's saying that any number smaller than s is not an upper bound. For the set A. So this statement is talking about something, to do with upper bounds. We know we're looking for an upper bound in our problem. Perhaps they're related. What I recommend doing is when you look at the conclusion of what you're trying to prove, the first thing I would make sure you know is what are you precisely looking for. So yeah, we're looking for a B in capital B such that B is an upper bound for A, but what does that mean? So I think it's important to write that out. So this piece, what that really means is we are looking for, so we want B in B such that for all A in A is less than or equal to B. That's what it means to be an upper bound for the set A. Now, the next thing that I would recommend doing is drawing yourself a picture of what we have in our situation, because we have a picture for how the lemma works, and maybe if we see what our picture is, it might make it clearer how we might want to use the lemma. So in my assumption, I'm assuming sup A is strictly less than sup B. So on my number line, if I plot where sup A is, that should be to the left of sup B. Now, if we think about what this means for our sets, remember that the sup of a set indicates the right wall of the set. So if I'm going to say that this is sup A, that means that A better live over here somewhere. And if the right wall of B is going even further to the right, that means that I should expect that the set B lives over here even further to the right. And intuitively, we would expect, there's got to be some little B and B in there, because otherwise, wouldn't the right wall of both sets just be the same, meaning the sups would be equal? So in order to say that the right wall is a little bit further past the right wall, the right wall of B is a little bit further past the right wall of A, there better be a piece of the set B that's coming up here in this gap. So notice that what I have here is a picture that has a gap, and I would like for there to exist an element in that gap. We've seen this picture before. It's similar to our lemma picture. Now, how things are labeled is a little bit different. So what I'm going to do is I'm going to take the number line from lemma 1.3.8 that we drew, and I'm going to write it right here. And I'm going to ask, who is playing the role of S in our number line? And then what about S minus epsilon? When you have these things lined straight up, lined right up above each other, it becomes clearer to see, well, sup B is playing the role of S, and S minus epsilon is sup A. So who is playing the role of S in our number line? This is sup B. And then S minus epsilon is sup A. So notice what that means for our epsilon value. Epsilon is always the measure, it's the measure of that gap. Now you could just take what I wrote down for S and S minus epsilon, and you could use algebra to figure out, or arithmetic to figure out what epsilon is, but it looks like the epsilon value we're looking at here is specifically the distance sup B minus sup A. Okay, let's take a step back. We have a bunch of stuff going on right now. We need to remember what the heck we were doing. So remember our goal. Our goal is to find a little b that is going to be an upper bound for the set A. And we discovered that means our little b, is probably, it's got to be something that's to the right of the set A. And we just got done making our little diagram, and we said, oh, this diagram looks really similar to the lemma. Really what we've got here is we're going to apply the lemma to B, to sup B, because that's the one that's playing that's the set that's playing the role of S here. And then here we have sup A. This is our epsilon. And the lemma is going to tell us that a little b has to exist right here. Okay, so let's go back. Now, we know in our lemma that S is sup B. We're given that we're talking about the supremum of B, which means that that's equivalent to knowing the quantified information that comes after the if and only if part. So here's what we know. We know S equals sup B. And so according to the lemma, because it's an if and only if statement, we now know that for all epsilon greater than 0, there exists a little b in B, such that S minus epsilon is less than B. You may wish to write this instead as sup B minus epsilon is less than B. Okay. What this is saying is our assumption is giving us a statement that we know is true for all epsilon, and our goal is to turn up this little b in particular such that it is in between sup A and sup B. So we need to use a specific value of epsilon to do that. Remember, we had a specific value. It was sup b minus sup epsilon. While we know that this statement is true for all epsilon, we want to work with a very specific value of epsilon to guarantee that the b we get turns up in the gap. Because if I were to use a different epsilon, let's say I used an epsilon that went all the way from here to there, like that, the number I get in the gap might be right here. And we don't want b right there, because we're looking for a number that's going to be to the right of the set A so that we can claim it's an upper bound. So we need to use a specific distance for epsilon to guarantee that the number the lemma returns is something we can assert is an upper bound for the set A. So I'm going to start writing up the proof for this, because technically we already have everything we need. So the assumption here is that sup A is strictly less than sup B. Now, remember what we said our whole argument hinged on. It was applying the lemma, and the lemma in particular, we were going to use it on sup B. So let's introduce what we know there. By lemma 1.3.8, and this is applied to sup B. For all epsilon greater than 0, there exists a little b in capital B such that sup B minus epsilon is less than B. So what we're going to do now is we're going to say, we know this is true for all epsilon. Someone hands me an epsilon, I can hand them back a little b. So in particular, I want to work with the epsilon value sup B minus sup A, so that the b I get is in the gap where I want it to be. So we're going to let epsilon equal sup B minus sup A. You might want to note here epsilon is greater than 0. That's because we started with the assertion that sup A was smaller than sup B. So for this epsilon, there has to exist a little b in B such that sup B minus epsilon is less than b. But what were we trying to do again? We wanted sup A. We were trying to say that little b was right here, and we wanted sup A, so here's little b. We wanted sup A to be to the left of it. So I really want to create an inequality that compares sup A to the number b. Because if b is bigger than the sup, then b has to be an upper bound transitively for A. So if I look at sup B minus epsilon, that is really, I can sub in what we chose our specific epsilon to be. And notice that that simplifies to sup A. But by definition of sup A, for all A in A has to be less than or equal to sup A. That's just using the fact that the supremum is an upper bound for the set A. And we can now say transitively that's less than B. Thus, by definition, what we've shown is that B is greater than or equal, actually it's strictly greater than any element in A. And that's the definition of an upper bound. B is an upper bound for the set A. And that was what we wanted to show.